So real quickly, just for the recording's sake, we talked about the AI project. Talk to me or look for feedback from me about how to connect it back to organic chemistry for part 2. The next part is a slight change in the course I'm posting into Canvas. How do I get out of this? Posting into Canvas some practice. Poorly labeled, but it's at least there. Shown there at the bottom, the week 6 docx, where you could go through and edit and put your feedback into it. You can use that for paper homework. It is not going to be graded, which I didn't actually say already. I'm not grading that. But if you want to use that as a source for paper homework, I'm fine with that. You can use it to ask questions. You come into class next week and be like, dude, I had no idea what the hell you were talking about. We can start with that. So we can help kind of ensure that you're running up to roughly weekly expectations. And then also for the sake of the recording, I'll try and increase active a little bit, but not a whole lot. Yes?
When do you think that the second part of the AI assignment is going to be due?
Did I not? I thought after exam 2, I think that makes sense. And I want to do it after exam 2 because this next unit is now dealing with the actual functional groups and how those things start to relate with other things. So we're starting to move into physical properties, and then we'll summarize chemical properties, and then we'll start actually doing, okay, here's a chemical reaction, here's the pieces that are moving around, here's what causes it to happen, why do we predict this, and all of that kind of, all that stuff coming together as one big thing. Okay, so I think doing the AI project after exam 2 makes a lot of sense, because then we'll start to get too specific into reactions. So yeah, other questions? Okay, so starting with this awful kind of flow chart, and you'll see a question in the I guess homework stuff that I put together. What you're doing is comparing two structures, and in that homework I went through and said, okay, here's two molecules. Redraw the molecule so that I can see it's superimposable. Redraw the molecule so I can see the mirror image. Okay? Redraw the molecule so you can identify the molecular formula. You're not redrawing it there, you're just summarizing what the formula is. Okay? And what was the other one? Atom connectivity. Redraw it such that the atom connectivity becomes clear where there's a difference. Does that make sense? So the intent being is that by going through and doing that and addressing all of those things, it's helping you to figure out how the flow chart kind of relates and moves through. Okay? Why is my foot asleep? So where I wanted to go, let's not do that one yet. Where I want to go is with this molecule, and we want to look at number one, identifying chiral atoms or stereocenters. There's a bunch of different words for it that technically are different, but I never understood the difference in definitions. So when we're looking at this molecule, what we want to do is find the chiral atoms. Okay? How do we know we have a chiral atom? 4 different things. So when we go through and look at this molecule, do we see any atoms that are connected to 4 different things? There are 2. Where are those 2?
What's it called, a tertiary carbon?
So that is a thing, referencing a tertiary carbon. Believe it or not, none of these are officially tertiary.
Because of the hydrogen.
Because what tertiary means, whoops, that looks like a horrible R. Tertiary, you'll also see me write it as 3 degrees, means connected to 3 carbons.
Oh.
Okay. I tend to not use that definition in the strictest sense, but that is the official definition. So when we go through and look at these, I would say none of them are officially tertiary. They're all secondary because they're all connected to 2 carbons.
Yeah.
When you say tertiary, I do understand what you mean. What you're talking about is this carbon and this carbon.
Yeah, the carbon.
Okay. And in that sense, I would say yes, I'm okay with calling those tertiary carbons. Because the whole point of our tertiary labeling system is really to actually reference not hydrogen. Okay? That's the important thing, because if it was hydrogen, anything else you're connecting now affects that carbon in a way different from hydrogen. So I want to address those spots kind of accordingly. So the tertiary, secondary, primary, and what I would call zeroary, okay, or methyl, are ways to label individual carbons so that we can talk about, number one, the strict definition, and number two, what their potential chemistries are. Since I'm more driven on the chemistry side of it, I would ignore the definition and say, kind of label these as quote unquote tertiaries. Does that kind of make sense? But if asked to label, according to a formal definition, everything is secondary. Make sense? Yep. Okay. So, can I come up with an analogy? I'm not sure I can come up with an analogy on the fly. I'll try and think if I can come up with an analogy. What I will backtrack it out to is I will never ask the question, how many tertiaries, how many secondaries, how many primaries are within a structure, so that we can avoid ever encountering that as an issue. Does that make sense? Does that help to clarify? Okay, because at least the two of you shook heads at me. Does that make it a little bit better? So in this case, okay, you're using the term, or she was using the term tertiary to help me identify where the chiral atom is. I understand what she's trying to say. The language is wrong.
That's right.
Okay, and that's where there's kind of a differential. Okay, so we will use the terms as our primary, secondary, tertiary to help us identify and talk about where chemistry is located, but I won't ask you how many primary, secondary, tertiaries there are in a particular exam question. And if I do, you can come back and yell at me. Okay, so if I asked on an exam how many tertiary carbons there are in here, you should immediately raise your hand and be like, dude, you said you wouldn't ask this. And I'd be like, damn, okay. Everybody ignore this question. Does that make a little more sense? Okay. So, chiral atoms. So those are chiral. How do we know those are chiral?
They're connected to 4 different
I only see 3 different things.
hydrogen,
Okay. There's an implied hydrogen to satisfy what?
octet,
The octet. What is the hybridization of those carbons?
sp3.
sp3. So if we're looking for chiral atoms, we can look for atoms that have 4 distinguishable things on it. We can also look for hybridization, because 4 different things is necessarily going to mean sp3. Okay? Just because it's sp3 doesn't make it chiral, though. We have to have 4 distinguishable groups. So if we were to look at these other carbons, they each have 2 hydrogens. The hydrogens are indistinguishable from each other, so those can't be chiral atoms. Okay. So the next kind of thing that scaffolds or potentially moves into this is that if we have these 2 chiral atoms, we have 2 different states that are possible for those bonds. Okay? We could have the chlorine wedged, or we could have the chlorine dashed. Okay? What does that mean as the possible ways that we could put this together? Well, we can reference a formula and say 2 to the n being the number of chiral atoms. So if we had 2, that's 2 to the second, which is 4. There are 4 ways that we could that we could draw this out, okay, to generate potentially different stereoisomers. Okay, so the stereoisomers are just referencing how many different ways we can assemble it. So the first thing we could go through and do would be to draw all possible combinations. If you're in a scenario where you're being asked to draw all possible combinations, what you should be trying to do is be as consistent as possible when moving through it. So if I go through and look at this, I can say that chlorine, we'll call it my blue chlorine now, could be wedged, or that blue chlorine could be dashed. So what I'm now specifying is those 2 possible states. Okay? My focus is now only at that blue spot. I should now also layer in the fact of the green spot. But to limit complexities, all I want to look at changing is the blue spot, which means when I go in and draw the next chlorine, I'm going to pick a steady state. In this case, I'm going to call it wedged. And now for both of those, I'm maintaining the geometry of that chlorine. Does that make sense?
Yeah.
Okay. And you're starting to move into kind of the potential next issue with it, and you're right. Okay. I now also want to address the fact that this chlorine, our green chlorine, could be dashed. Okay. So now I have to go through and draw in those states. Okay. So in that top case, I want to maintain. So now what I'm looking at is the left to right connection. It's a horrible arrow for the record. We'll come back to that later. Okay. And I'm saying that that chlorine could be dashed. Okay. It could be wedged or it could be dashed. Okay. We will also get the scenario where that chlorine could have been dashed here. And again, since we're now looking left, right for the bottom set, we're maintaining that chlorine. So as we built this out, we started first looking top, bottom, comparing, then right, left, and then right, left for the second set. Does that make sense? Okay. This way, what we're trying to do is show all possible relationships without being like, did I count that one already or did I not? Okay. And that's going to become super important when we go through to look at the relationships between these. Okay, so the whole point of this, or not whole point, but one of the big points in this unit is first recognizing chiral atoms and then recognizing how complex it could get when we're trying to identify the relationships between these. So now we've got a bunch of different things that we can compare. So let's start by comparing these two structures. Okay. Do they have the same molecular formula?
Yes.
Yes. What's the next question in the flowchart?
Are they superimposable?
Are they superimposable?
No.
Okay. I'm going to take this black part and try and overlay it on top. Okay. I would argue the way these are drawn right now perfectly allows me to see if they're superimposable. I don't have to do any manipulations because the carbon structure overlaps. I've got my chlorine up and I've got my chlorine there. They're all in the exact same relative locations. When I do that, everything superimposes, right? Green superimposes, black superimposes, but blue does not. Okay? So they are non-superimposable. Okay, that's now established. What's the next thing I should look at?
Atom connectivity.
The atom connectivity. Okay? Are the atoms connected in the same places?
Yeah.
Yeah, so we could pick a position. If we start with our chlorine up, okay, call that 1. If we go counterclockwise, that's position 2. Position 2. So if we were going to name this, we would say we had a dichloro 1 and 2. So 1, 2, dichlorocyclopentane. If we're getting the same name through that process, yes, they have the same atom connectivity. Okay, what next?
Is there a chiral atom?
Do we have chiral atoms?
Yes.
We already have that answer because that's how we started this whole premise. Yes, they had chiral atoms. We've got 4 distinguishable groups connected to it. Okay. Note, what was something that could potentially help us? Do we see wedges and dashes? If we have a chiral atom, theoretically, we should be using wedges and dashes. Does that mean when you see a wedge and a dash that it is chiral? Not necessarily. Theoretically, yes. If you're using wedges and dashes, that should be signified for a chiral atom. Why is it not always true? Well, it's not always true because of you. It's your fault. Okay? Because when chemists use wedges and dashes, they use it for chiral atoms. But you will make the mistake of using wedges and dashes kind of sporadically or randomly. It's not incorrect to use those wedges and dashes all the time. It's just not useful to show it that way. Okay? So it's your processing by showing wedges and dashes kind of when it's not necessary. That means we have to call attention to the fact that wedges and dashes don't mean chiral, okay, because you use them incorrectly. Kind of, sort of? Okay, so We had chiral atoms. What's next?
Mirror image.
Okay, are they mirror images? Okay, this becomes a harder question to go through and evaluate. Okay, for me personally, I'm going to erase this starting thing over here and all these words. For me personally, what I would go through and do is draw a mirror image. Just immediately go in and say, I don't see the mirror image, I'm going to make a mirror image. Okay, I can do it with either structure, it doesn't really matter. But I'm going to go ahead and take this molecule and I'm going to draw the mirror image right here. Okay, so here's my mirror plane. What am I going to encounter? Well, the first thing I would see, let's see if I can actually pull this off, right? There's the C, there's the L. You kind of get the point,
Yeah.
right? And yeah, you can laugh and say that looks kind of stupid and all that, but what I'm really trying to accent is the fact that we're looking at that mirror image. Whoops, and I'm looking at the wrong one. CL, so we can fix that. Yeah? Okay. So I now know this is a mirror image of that structure because I just drew it. Does this structure superimpose on this one? Well, why do I want to ask that question? If you go back through the flow chart, what does it mean when they superimpose? That they're identical. Okay? So this I know is a mirror image. If I can change this manipulation so that it superimposes on this, I know these two are identical. And if I know these two are identical, I now know these two are mirror images. Okay, because I know that one was a mirror image. And I just realized all of that was talked through and not written in any way, shape, or form for someone watching in the video. Sorry. Okay? So, now that we've got this, does it superimpose? Okay, well, how would we figure that? If we just take that carbon structure and we slid that over, everybody sees that the carbon backbone does superimpose. Okay, yes. Yeah? Okay, the chlorine, green chlorine, actually superimposes as well. Does the blue chlorine? No. Okay, the blue chlorine is showing up on the complete wrong side of the molecule. So what do I want to do? I'm going to take this molecule, and as you were kind of gesturing, Shay, is I want to take this and I want to flip it over. Okay, so when I flip this molecule over, this was my mirror. I'm going to flip. What happens? Okay. If I'm flipping along this axis, what happens? So if I take that and flip it over, where's the chlorine now? It's on the left side. Awesome. Okay. So my chlorine should be over here. This was wedged at me, right? When I flip it, ooh, it's dashed. It's going away. Okay. Dang, so they do superimpose. Why are you shaking your head?
The chlorine is also dashed now.
The other chlorine that was wedged is now also dashed. So that when I now go through and draw that one on, what happens? Yes, my blue chlorine now superimposes, but the green one does not. What does that mean? Yes, sorry, I was processing different spots. Okay, the structure we've done at the flip, okay, we'll call it A and B are not superimposable. Okay, since they're not superimposable, they're not identical to each other, which then means, we're running out of letters, C and B are not mirror images. Make sense? Cool. That's all the permutations. Those permutations are dealing with a three-dimensional model, spin, flipping, and rotating in space. That's why Unit 1 was supposed to be driving all that. It's very challenging to deal with those spatial manipulations. The whole point there is to go through a whole bunch of drawings so that you can see those changes. Right? So cool. You said they are not mirror. I don't want to erase yet. Right? We're still trying to define the relationship between what I've defined as C and B. So they're not mirror images. What does that mean? They are diastereomers. So we've now identified by moving through diastereomers the relationship between those two structures. We good? Okay. Which then means, what do we got to do? Whoops. All of that work is now not necessary anymore. And now what I would go through and do is identify the next relationship. The next relationship. The next relationship. The next relationship. All of those arrows are now different relationships that you could get. This was one single molecule-ish that we started with. There's 4 different representations, and now 1, 2, 3, 4, 5 different ways or relationships that we could discuss. Kind of, sort of? And?
Why don't you make an arrow go that way?
Oop, fair point. I missed that. Yeah, I think I want that. And that pause and humming that may or may not have been recorded is me attempting to do all these spin, flips, and rotations in my head to figure out those relationships. Okay? So if I did this all correctly, you'll note that some of those colors for my arrows are the same, some of them are different. Okay? That was done, hopefully, correctly, intentionally. And so if we go through and now look at the relationship on the other side, okay, the red arrow, okay, superimposable, or we could go through all of our systems, same formula. Do they have the same connectivity? Are they superimposable? Okay, and what we will find is that indeed they are non-superimposable and they are not mirror images, which means the relationship is diastereomers. Okay, that one I was pretty confident on. It's the other ones I'm nervous about. Okay, if we take a look at purple, oh fudge me, I can already see that I'm wrong. Okay, if we look at the top relationship, actually maybe I'm not wrong. Nope, I am wrong. Okay, now I'm right. Okay, if we go through and look at this relationship, we can see that we get some superimposability and we don't get others, which then means that's also going to be diastereomers. And the bottom one's going to be the same issue. Okay, so now our crosses through the middle. All right, let's take a look at the black one. Okay, if we look at the black arrow connecting those.
Non-superimposable, but they are mirror images.
Okay, they are indeed mirror images. I completely give you that. I guess I shouldn't have deleted that one. Okay, but then you're also saying non-superimposable. Why are you saying non-superimposable? What happens if I take, I have to do a couple manipulations. If I take this molecule, actually I don't have to do a couple, and I just flip it over.
Then the chlorines are dashed. But is it the same thing?
Answer the question that's asked, what happens to the superimposability? They are superimposable. Okay? So these two are mirror images, great, and those two are superimposable. So you say, oh, okay, well that must mean an enantiomers. Except, what's one more thing that we've got to watch out for? And the colors might be throwing you off on this. So we got all those mirror images, so I'm going to get rid of all that.
Are they identical?
Instead of doing that mirror image, I'm just going to take structure C and I'm going to, which direction I want to do. I want to flip along that axis. So that would be there. That would be there. Everybody agree?
Yeah.
You okay with that? Okay, and you'd be like, well, those aren't why aren't those superimposable? On the diagonal? That's dash, dash. What is this? Dash, dash. There it is. The colors. Why do we have these shown as different colors? So that we could see where those individual pieces were. Is chlorine different than chlorine? No. There is no difference between chlorine. They're different atoms. I can't tell a difference between them because they aren't labeled. Okay? When I look at an individual molecule, it's not green and blue. Okay? I can't see that difference. The only reason we used the colors was to help us track those individual positions. Okay? So we used those colors to help us ensure that we found all of those pieces. We have to realize that it's black and white. Okay? And if it's black and white, what is the relationship between this guy and this guy? They're superimposable. Well, what was the relationship between this one and this one? They were identical. I just flip it over. Which means these two are superimposable. Which means these two are identical. Does that sting a little bit? Yeah, I would argue it does. For me, personally, I think it stings. Okay? The colors were used as a cue to help us launch where those things were so that we could kind of keep track of those positions. We have to realize that that was an artifact of us. Okay? When we're flipping that molecule over, I can't tell which chlorine is which. They aren't different or distinct from each other. So, well, one is to the left of the other. Well, it's still to the left of the other. Okay? That hasn't changed. Does that kind of make sense? Okay? So the relationship on that black diagonal is that they are identical to each other.
But they also have two chiral atoms.
Which is where I was going to go to next. Because of course it can't be perfectly simple. They still had two chiral atoms. So if we're looking at a molecule, okay, that superimposes on its mirror image and has two chiral atoms, we don't call it identical because what we're trying to do is identify that it has this extra layer of BS and chirality that I don't want to have to deal with, but I'm trying to layer that information in. We call it meso. Okay? So on that black diagonal, those are identical molecules. I have to call one of them meso. I wouldn't draw the other one because what we're trying to draw is all possible. Those aren't different from each other. Okay. Go ahead.
I don't get how they're identical.
Let's try this.
Well, I'm not confused with the color. I'm more confused, like, because if you had it like this,
Whoops.
if you had it like this, and you turn it over, wouldn't it be like this, wouldn't the chlorine be on the other side?
Mm-hmm.
Or is it not?
So when I do the flip of this molecule, C, I get this structure. What you're flipping on is this axis. I'm flipping on this axis. I don't know how.
The top one's gonna be down.
So this top one now when I flip is going to exchange across this half, that dividing line, and that top one's now going to be over here. This one's going to be over there. This one goes over there, this one goes over there, this one stays in the exact same spot. So when I make that flip, this atom never changes its location, it stays right there. Everything else reflects across it.
Okay,
Do you see it?
yeah.
Other questions on that one? Okay. Now the mind bender one for me personally is what's happening on the blue one. What's happening on that blue line? Okay, and we'll start to actually, and by start, we'll actually go in and remove the color coding of our chlorines. Does the carbon ring overlap? Yeah. Okay. Do the chlorines overlap?
What do you mean by that?
So if I take this lower left hand and I bring it up here,
No.
okay, that top chlorine, dashed versus wedged, wedged versus dashed, doesn't superimpose. Everybody see that? Okay. If I take this bottom structure and now I rotate it, I'll get my chlorine to be dashed, right? What happens to the other chlorine? So
Okay, that
if
one.
I'm taking this molecule and I do the rotation clockwise, I'm taking this chlorine that's dashed and I want to bring it up. What happens to this chlorine? Where should I be drawing it on that new drawing? Does that superimpose? Now the chlorines are located in the wrong spot. Guess what you're going to find? There is no way that you will be able to superimpose those two structures. You can spin, flip, rotate, do whatever you want. They will never, ever, ever superimpose. Okay?
Even if you do the same thing that you did with the one above it?
Yep. You want to flip it over. If you flip it over, the chlorine's now on the opposite side. You'd have to turn, and what you'll find is that as you turn it, you'll never get it back to that spot. Okay? Is that mind-breaking? Yes. This is the one that I think is most mind-breaking. Okay? And it becomes easier to do the manipulations if you build it with a model kit. So you build those out with the model kit, you're not trying to redraw all of the possible rotations and spin flips, but you're now just taking the model kit and very quickly testing them all to realize there's no way in hell that you can ever do it. Okay? So they are non-superimposable. Right? Well, the diastereomers were also non-superimposable. Okay? So how do we differ? Is this a diastereomer then? Is the blue one now a diastereomer? Well, we've color-coded it, so we could probably say no, but we got to prove it. What's the last thing that we have to check? Mirror image. Okay. Let's not do that one. So let's drop our mirror image down over here, our mirror. And if we did that mirror, yeah? Now what we want to do is see, does that superimpose on my lower left? Well, initially we might be like, nah, it doesn't. But if we'd taken that one in that lower left and done what we'd written out here, this is why I didn't erase it, and we just rotated in the plane of the paper, that's what it looks like, that full rotation. Interesting. The lower left and the upper right are identical. The relationship between the upper right, this guy, and that one was that they were mirror images. What does that mean about the relationship between, we'll call it A and B now? They are mirror images. They are both mirror images and non-superimposable, which then means the relationship between them is enantiomers. Enantiomers are the relationship that is the most challenging to differentiate. Okay? And the only way we can differentiate enantiomers is by bringing in another chiral thing. Did we ask the left-handed question? There were a couple people that were lefties, right? Or was that? No, nobody was. Yeah, that's useful. Okay? But if you know a lefty, they usually complain about scissors. Okay? Why do they complain about scissors? Scissors tend to be made for right-handed people. Okay? And lefties have a chirality. Our hands are chiral. They're non-superimposable mirror images. So if we design scissors for a right hand, we're designing something that is chiral. That interacts incorrectly with the other hand. So the only way we can differentiate chirality is by introducing more chirality. Okay? Why is that important? That becomes important because most of the stuff we do is achiral. The table is achiral. The chairs are achiral. Your pencil is achiral. All of that stuff doesn't have chirality, which means lefties and righties can use it. There's no problem. It's only when a new chiral thing gets involved that it becomes problematic. Why do we care then at all if most of the world is achiral? Well, not most of the world is achiral. Most of the world is actually chiral. All of biology is chiral. When you talk about your amino acids, someone's going to have to help me on this. There's a reference to amino acids, and we usually call them D or L amino acids. No one can help me out on that. Seriously?
I swear to God, I learned about
Damn
that
it.
so long ago. It's
Yeah, me
gone.
too.
It's
I don't
gone.
remember. But when we talk about our amino acids, we only talk about one of them. That D and L is in reference to the chirality. All of your amino acids are chiral. Well, amino acids make up what? 100, not 100%, some absurd percentage of the human body, which means if we introduce a drug that's also chiral, that drug is now going to have different interactions depending on which handedness we designed it for. That's a really big deal. And that's why thalidomide had such a big problem. We look, it's just a different hand. The other one we just won't worry about. Well, the other hand turned out to be a mutagen. That's a really big deal. And we don't see how that manifests until we go through lots and lots of tests, which is one of the reasons why drug processes going from discovery to market is a very slow process because you have to test all of those secondary features. Right? Naproxen has two forms. I don't remember what they call them. They might actually call them R and S. Naproxen. One of them is a straight up liver toxin like death to your liver. The other one is whatever it is, pain relief, muscle relaxing, right? So you only get one. If you look at your bottles of naproxen, it actually states on it S naproxen. It doesn't say just naproxen. It has to be very clear because if they give you the other handed version of that molecule, it causes lots of secondary side effects. So it is a really big deal. And it's not easy to see. Diastereomers have different arrangements of atoms, right? That vastly changes their intermolecular forces, how they interact with the world, which means I can test and see those differences instantly. That's very easy to deal with kind of in the open world. But enantiomer is not so easy to differentiate, and I have to bring in more chirality to actually be able to figure those things out. So if we're talking about how we run chemical reactions, we will run chemical reactions where we can produce enantiomers. Generally speaking, that's an awful reaction to run because that's producing two products that I cannot separate easily. And if one of them is a toxin, that's really problematic. So when we get into talking about running chemical reactions, we try to focus on reactions that only produce one product. Not two. Kind of, sort of? Okay. That looks awful for the record, but we got it?
Yeah.
No, you're still drawing it? Okay. And I would highly encourage, as at least one of your classmates is doing, is building model kits so that you can see these relationships and make that more apparent and real to you. Okay. Kind of, sort of? You're good now. I was going to be like, check minute 39. Okay, so if you needed to copy that down later. So the next thing that I'll kind of mention again, and I'm a little on the fence on whether I would ever test on it, is that how many possible stereocenters can come, or stereoisomers are possible. So when we run a reaction, we're starting usually with something very simple, and we run multiple reactions and keep adding to it and adding to it. If there's chiral atoms in it, those chiral atoms now create branch points where we get multiple possible products. So if we look at simple drugs that only have one chiral atom, like naproxen, great, there's only two possible results. Theoretically, I can separate two things from each other. But if you have three, you now have 8. That's becoming significantly harder to separate away. And when we look at our really complex kind of anti-cancer drugs, they're upwards of 10, 11 chiral atoms. Okay? So you're looking thousands of possible ways that you could be creating bad toxins that you have to be careful to eliminate those issues. Kind of, sort of? Okay, but yeah, that's that formula, just 2 to the n. There is also this -1 mirror plane. I definitely wouldn't ask about that. So if we looked at a molecule like this, I looked up something that I'm sure was a drug, and I don't remember what it does. Any pharmacists? No? Okay. How many possible stereoisomers could we get? So what's our first task? Find the chiral centers. Where do you see chiral centers?
The NH one?
The nitrogen?
Yeah.
You have to have 4 distinguishable groups.
There's not even a carbon there.
Okay? So our kind of baseline is it should be a carbon. Okay? Nitrogen can officially do it, but it's a bit of a challenge to get things.
Carbon next to the nitrogen.
That carbon? Oops.
On the left.
That, okay, fine. Okay, that carbon, is that a chiral carbon? Okay, you're saying no, why?
Isn't it connected to 2 carbons, which is the same group?
True, it is connected to 2 carbons. Can you tell a difference between those 2 carbons?
No.
You're telling me this carbon and this carbon, you can't tell a difference between. Okay? And it's a little more than kind of. This top carbon is connected to a giant ring. Is that bottom carbon? No. Okay? So they are different from each other. They are distinguishable. The next part is how are they distinguishable, and that's a whole other can of worms. That's dealing with RNS. We'll see that in a second. Okay? Does that kind of make sense? So that carbon, but that's only 3 things.
Then hydrogen.
4th, there's an implied hydrogen. So that has 4 distinguishable groups. Yes, that is a chiral carbon. And for the sake of timing, that's another one. So there are 2 chiral carbons in this. So for this particular drug, there are 4 possible stereoisomers that we could get. And that was it. Okay, 2 to the n. Okay? What's the head shake? Which part?
Isn't the one on the right also chiral?
That carbon? Okay, we have to have 4 distinguishable groups. What are the 4 distinguishable groups connected to that carbon? I've got oxygen, nitrogen, carbon.
Oh, there's no. Oh, okay.
And there's no implied hydrogen because
There's no.
there's the double bond. Okay? So then the thing that I really, really don't want to talk about is now how do we differentiate? Once we've found that we have this difference, if we look through the naming systems of it, we talked about same atom connectivity. We come to the exact same name for compounds that have vastly different properties. Okay? That's an issue. So we have to create a naming system that allows us to differentiate. Okay? That naming system comes back to a rule set called the Kahn-Ingold Prelog rules. This is how we would define RNS and also how we define cis and trans, believe it or not. We just picked relatively simple examples of cis and trans so we didn't have to worry about it. Okay? But RNS becomes the more challenging application of it. So first thing we would do is we would zero in on our stereogenic center. So there it is. Okay, we're going to look at the left one. Okay, so when we look at that left one, we now want to assign a priority to the 4 groups around it. That priority is based off of atomic mass. So if I go through and look at this, I have nitrogen, I have carbon, and I have hydrogen. Atomic mass. Okay? Is there a difference in those atomic masses that would allow me to start to assign numbers? Yes. Okay? The numbers we pick are 1 through 4. We assign the highest priority number 1. Nitrogen has an atomic mass of 14, carbon is 12, hydrogen is 1. This means nitrogen gets our 1 label. Do I have another number I could put in there?
Go to the carbon with the oxygen one.
So we could go to the carbon, but I would argue you're not going to be able to differentiate the atomic mass between carbon and carbon.
Okay. But don't you normally go?
We'll have to deal with it, yes. How about hydrogen?
Hydrogen's usually numbered.
This is going to be 4. It is the lowest atomic mass, so we could go through and we could assign a 4 to it. Okay? Take advantage of the things that we can get while we can get them. Okay? So now between purple and blue, that's carbon versus carbon, they have the same atomic mass. How do we differentiate? Okay? It's still atomic mass. I go out to the next highest atomic mass from those spots. From the blue one, what's the highest atomic mass from the blue one? It goes out to oxygen and nitrogen. Which is the higher one? Oxygen. Okay, so oxygen comes in at a 16. For the purple one, I'm going out to the next highest atomic mass. What does the purple one go out to? Carbon and 2 hydrogens. Do I care about the hydrogens? No, because carbon's the higher atomic mass. So I'm now comparing blue 16 to purple 12. Which one is a higher atomic mass? Oxygen, which means that blue carbon gets assigned the 2. The purple carbon gets assigned the 3. Okay? Now that I've got all my numbers assigned, now what I would go through and do is ensure that my molecule is oriented in a fashion that the lowest priority, so my 4, is aimed away from me. How would I know it's aimed away from me?
Dash, sorry. You know what I meant.
We have to ensure that our lowest priority is aimed away from us. It should be dashed. There's a reason I picked this molecule and not the other one. Okay? So it is indeed aimed away from us. Once it is aimed away from us, we then can move kind of clockwise, or not clockwise, move our arrow, or draw an arrow going from 1 to 2 to 3. So 1 to 2 to 3. Right? I wouldn't go this way, 1 to 3, because now 2 comes before 3. Does that make sense? Don't laugh at me. That was rude. Okay? And particularly for something that's obnoxious like this. Okay, so cool. Which direction am I moving that arrow? I'm moving it in the clockwise fashion. What does that mean I will do? That red stereogenic center, I will now call R. Why R? Right begins with R. Yeah, give me whatever look you want. Whatever you can remember is fine. I don't care. Okay? What happens if we go over to the other one? Oh, actually, because they drew it nicely. Conveniently, we could go through the exact same kind of labeling system that we've got. Our nitrogen came in at 1. The one with the oxygen up top came in at 2. We had a 3, and we've got our hydrogen at 4. We'd go through the exact same process. I go from 1 to 2 to 3. That's moving counterclockwise. I would call that center S. Okay? Some added complications to be aware of. Which way is my hand moving?
Counterclockwise.
Counterclockwise. Are you sure?
Yes.
Which way is my hand moving?
Clockwise.
You just said it was counterclockwise.
That's what you're looking at.
Did I change the direction my hand was moving during that process?
You change the direction you want.
You changed your frame of reference on it. Your frame of reference for assigning R and S is critical. You have to be aligned in the proper viewpoint to assign R and S correctly. Okay? I just talked through all the rules, but we didn't have them up there. Can I erase everything up here?
Yeah.
Okay, and the rules, come on, close. Should be on the next slide. Here they all are. You identify your chiral atom, you assign your priority, okay, based on atomic mass. There's rules for assigning it. We go to higher atomic mass equals higher priority. What if you didn't see a difference? We had carbon versus carbon, right? So what did we do? We moved to the next atom. Officially, we moved to the next atom with the highest atomic mass, right? Still no difference? You continue to move through until you find a difference. If you don't find a difference, it wasn't a chiral atom in the first place, okay? If there are multiple bonds, this one gets a bit nasty. I won't ask. Right? If you go online and test different things online, you will see that they will talk about multiple bonds. Each bond in a double bond is counted as another of that atom. Okay, so you end up adding ghosts or phantom bonds in your drawing. Assigning RNS only works really through sp3 atoms, and if you have a multiple bond, that's sp2 or sp. So you have to convert those atoms into sp2 or sp3. Okay, so you create phantoms. But I will try my very best to not ask a question about that. I can almost guarantee I asked it in the homework. So we'll practice it in the homework. I won't ask it on an exam. Right? You then have to orient the molecule so your lowest priority is aimed away from you, and then you connect an arrow 1, 2, 3. Right? So note in this case, our dash aimed away 1 to 2 to 3. The direction we're moving is clockwise. We assign that one R. Okay? Lowest priority aimed away 1 to 2 to 3. Low direction we're moving is counterclockwise is S. What if your drawing doesn't have the lowest priority aimed away from you? You have to redraw the molecule by spin, flip, rotating it so that the lowest priority is aimed away from you to make the assignment. Okay? There are lots of shortcuts that I've seen online that say, oh, all you have to do is this. Okay? Those shortcuts, for me personally, because I've used a bunch of them, because I hate having to go through this whole process. I've used a bunch of them. They are successful 50% of the time. There are only two answers, R and S. If the shortcuts are successful 50% of the time, what is happening?
Might as well just guess.
You might as well just guess. Right? I'm not convinced the shortcuts are broken, and it could very well just be me who is broken and doesn't know how to use them appropriately. But every time I've used a shortcut, I'm down to a 50-50. Right? So be very careful using shortcuts with this, because I don't trust them to actually work the way they're supposed to work. Right? Which is the other added complication with this. You may go through and say, oh, this one's R, and you check your work, oh, it was R, I must be right. Not necessarily. It was a 50-50 coin toss. You could have just luckily guessed it as well. So you're going to be very careful when assigning RNS. Kind of, sort of? Okay. With that, I'm pretty sure we're done with these slides. Oh, there's potential practice to assign. We'll do the lower left-hand corner as practice, because this brings in the double bond. So if we look at that lower left, we've got hydrogen, we've got carbon, and we have carbon. Okay? So right away, hopefully you can see that the hydrogen can get labeled as 4. Okay? How do we differentiate the carbons? Well, the blue one goes out to hydrogen. What does the green one go out to?
Carbon, 2 hydrogen.
Green one is, I'm only going to the highest priority thing. Okay, so for the blue one, it only goes out to hydrogen. Yes, there's 3 hydrogens. I don't care about the other 2 because it's only going out to hydrogen. The green one goes out to a second carbon. That would be this guy. Okay, what does the red one go out to? Carbon. Okay, what does that do for me? Do I have a difference yet?
I mean, the difference between blue.
Yeah, the blue one is differentiated. The blue one has the lowest of that set of 3, which means the blue one can be assigned a 3. Lowest of the set. I already assigned 4 to the hydrogen. Okay, which is why we have to be careful and track. And now we kind of set up with the next issue. What do we go to now? Well, that red one is a problem, because what is that red one? That's a double bond, and we said the double bond becomes tricky to deal with. Okay, so what we do with that red one is we have to convert it into the system that is sp3. So that pi bond is now a phantom to a carbon. Okay, so that bond is there. Officially, if I needed to, I also have a phantom out at the other end of that pi bond. Okay, why is that important for me? So now when I go through and compare my green to red, we start at the red and we're starting at the green. The green one goes out to carbon, star. The red one goes out to carbon, star. Yeah? What does the green one go out to next? Hydrogen. Okay, I'm not continuing further on the chain. I'm addressing all of the bonds around that carbon. What does the red one go out to? Another carbon. What's the difference between carbon and hydrogen? Is there an atomic mass difference?
Yeah.
Yep. What does that mean?
Level of the red one, 1.
Red one gets 1, the green one gets 2. My lowest priority 4 was aimed away from me. It's now moving through my circle. I'm going 1 to 2 to 3. Which direction am I moving?
Counterclockwise.
Counterclockwise.
S.
S. Kind of, sort of. And if you're looking at that being like, that's not that bad, you clearly have not done enough practice. Because it sucks. Okay? So yeah, with that, that should be okay for whatever we said, hopefully helping with active. And I'm not positive, but I'm fairly confident that I asked one. And I will try my best to not ask an exam question on assigning R and S with double bonds. Okay? I don't have to, so I can shift away from it. R and S, if you have to take biochemistry, you'll encounter structures that look like this. You may have already encountered structures that look like this. This was the Fisher projection. Okay? How do we get to the Fisher projection? You take your standard normal line angle, and then you have to change your viewpoint slowly all the way through. This is what that drawing video did, right? Okay. Kind of makes sense how we're aligning it. So the Fisher projection, oh, come on. For whatever reason, I guess I decided to hide it. The Fisher projection, officially, every horizontal line is a wedge. Every vertical line is a dash. Why is that useful? If I've defined that, I don't need to show wedges and dashes. That's why Fisher projection shows us. Okay? Extra added benefit that we'll go through and do is that if you assign R and S on this, what you're going to end up finding for that top carbon, it's R. For the next one, it's S. For this next one, it's R. For the next one, it's R. It's not that it alternates. What did R mean? What was the other option? If we're turning things clockwise, we might say that we're turning it to the right. If we turn it counterclockwise, we're turning it to the left. Anybody speak German?
No.
No? Guess what left is in German? Something that starts with an S.
Okay.
Okay, I'm not sure that's actually true, but it's close enough. Okay, the R and S, I believe, are actually German tied, and it's referencing which side of this drawing your highest priority group is located. So Fisher designed this system so that he didn't have to do a whole bunch of this extra work with R and S, which is kind of neat. Okay, but at the same time, you get a bunch of other changes that go on, and it can make things messy, and we can ask questions that break that system.
just
Try
looked
it.
up German, up in German, it's not.
Oh, it's not S? Okay,
No,
what's,
it's
what's,
links.
it's links? Oh. Well, I don't remember.
I was just curious.
I'll have to backtrack what the S meant. I forget. Oh, sinestre. Sinestre for sinister. Who's the most sinister person?
Lefties.
Think biblical. Why are lefties sinister?
Something about that one. They should be righties.
Cain. Cain is left-handed. That's why nobody likes lefties, because Cain was lefty.
John McCain?
Cain. Allegedly. According to the Bible that I've never read. I've only heard rumors, to be honest.
You've heard
But-
rumors of the Bible.
But I'm pretty sure that if you look it up, Cain, I was going to say Adam and Cain. It's Abel and Cain, right? Okay, so see, someone can back me up. Why aren't, just let me flounder through it. Okay, Abel is right-handed and Cain is left-handed.
And
I
Cain.
believe is actually referenced, and Cain is the one that like kills people. I don't know. Yeah, see,
And
there
then
you
he
go.
does it with his left hand.
Because he's sinister.
Yep.
That's where it is. That's why it's S. And that, I think, is actually somewhat legitimate as a reference, just for the record. Somewhat legitimate. Okay? So, you do have to go through and do this, but yeah, this is one of the things that's kind of cool. You see this notation all the time in biochemistry, because that's a lot of chiral atoms, and what you'll find is biologists get confused with three-dimensional shapes. I apologize, that was the wrong audience for that joke. But get confused with three-dimensional shapes, and so we try to simplify it as much as possible so that we don't have to think about or draw those things that way. Okay, which makes perfect sense for the record. Okay, I accept that. So we'll get R and S. I do want to mention that you can hear reference to plus and minus. Plus and minus are not R and S. It's an entirely different system. Plus and minus is an experimental observation of chirality. R and S is us looking at a structure. Ideally, those two things would align, and they don't. Okay? You will also encounter, if you have to take biochemistry, reference to D and L. D and L also has no reference to R and S. But lowercase d and lowercase l do. Yay! And it's all going back to chirality. So if you're hearing different references for the different forms, D and L or all those, just slow down a little bit because you're looking at chirality and that can be a mess. Kind of, sort of?
Are there going to be Fisher projections on the next exam?
You are responsible for interpreting Fisher projections,
Okay.
is where I will go with that.
Like interpreting R and S, or like what?
Yes.
Just that.
All of it, yes. Fisher projections are a drawing that you are responsible for interpreting. So you should be able to get from a Fisher projection to anything else. How many times have I shown different ways to get through it? Did I show you how to go from Fisher to line angle? Arguably I didn't. I said line angle to Fisher. So if I asked Fisher to line angle, you could be like, stop being a twit. And you have an argument that you would probably win, if I'm going to be honest. This last thing I only include because if you move into biochemistry, you could see something like this. What you're referencing is all the carbohydrates. All of those were chiral atoms, so you can look at all the possible combinations of the chiral atoms, and it generates that many different stereoisomers. So it's kind of neat, or I think it's kind of neat, as long as I don't get tested on it. And I've been tested on it. It wasn't pleasant. So the next thing I kind of want to get through, I know in like 30 seconds, is there was the play pause it video, which you should have watched. So theoretically, all of this is review just from the video. It should also be review from whatever prerequisite course you took, either Chem 151 or 130. We've got our intramolecular bonds. Ionic, polar covalent, and covalent. We've already talked through rules for how we establish what those are. It is important to be able to look at a structure and identify which bond type you have. Because once you identify the bond type, you can then start to say how that interacts with other molecules. Okay? And we can now say, oh, this is a good interaction, this is a bad interaction, this is a strong interaction, this is a weak interaction. And as long as there's big enough differences, we could now arbitrarily go through and define the types of intermolecular attractions. I would argue there's 4. Okay? So you should be able to identify those by looking at a single molecule and being like, that's going to have hydrogen bonding. I know hydrogen bonding is a strong interaction, which makes it a very polar molecule. If that's starting to ring some bells about lab, that's because it should. Everything we've done in lab is intermolecular forces. Every little bit. Okay? Don't worry, Shay, I've done a trash job pointing it out in lab. Okay? The big interaction that I want you to be kind of aware of is this kind of color wheel that I want to talk through before we completely kind of disperse. Really what we're looking at here is if we take this and turn it into a straight line. This is a continuous ring. Not quite continuous. It's continuous through the top. Okay? And what we have done is really just said that we have a spectrum of very weak interactions at one end and very strong, I guess officially strong interactions at one end and weak interactions at the other. Okay? And we arbitrarily kind of looked at that and said, well, if it's stronger than this point, I'm going to call those chemical bonds because they are sharing electrons. And if it is weaker than that point, I'm going to call those forces. Okay? That's all of chemistry right there. Now everything we do is how do we quantify where we're at in either forces or bonds. But that's it. That's all chemistry is. Right? What's happening to get to this diagram is I've taken that thing and I've now bent it in a circle shape. Why? Because if I have a very strong chemical bond, right? If you've got friends that are, or couples that you know that are really strongly attached, how often do you get to see them? Not at all, right? Because they're happy with each other, they don't want to see you. Okay? Their interaction with another system is very, very weak. But if you get couples that aren't strongly connected, they're now more social and they will see other people. Okay? The interaction you're now seeing in that other environment is now a stronger attraction. So if you can identify the type of bond, you can then identify the type of force, and we know something about the strength of that attraction. Right? Why is this important? Phase changes. All phase changes are dictated based off of intermolecular forces. If I want to look at a chemical reaction, why does the chemical reaction change bonds? It's because I'm looking at a really weak bond and I'm turning it into a stronger bond through a chemical reaction. So if I can look at molecules and identify these pieces, I can start to make amazing predictions about what's going to happen with very little chemical understanding. And that's beautiful. Okay? So what we'll do is talk about this next week. All of these things kind of list out. Most of these are old stuff for Gen Chem. Phase transitions will be important for us. Melting points, boiling points. Solubility is going to be important for us. And reactivity is going to be important for us. We'll start with solubility and phase transitions next week. And we'll look at reactivity probably in 2 weeks.